cases, back to using thermodynamic values to calculate different things. And this one kind of, requires you to maneuver your way through a variety of different equations, right, to get the different values that you're looking for. So looking at this right here, right, we're looking at, half of chlorine gas plus half of, fluorine gas forms CLF gas. In these cases, we're given K values at two different temperatures, one at 25 degrees Celsius, one at 125 degrees Celsius. And the first step is to calculate what delta H is, delta S, and delta G at 25 degrees Celsius in these cases. So there's two things that we can do, two approaches that we can do, right? So first things first, we can just simply calculate what the delta G is. In these cases, right, that's probably the simplest thing to do. So the delta G not value, right, is going to be at 25 degrees Celsius, right, which is the standard temperature that we should be doing this at. And that's going to be, equal to negative RT natural log of K. And so we know what R is, right? We know what T is. We know what the natural log of K is. And so we can get the delta G value then at standard conditions. So if we take that, right, so negative 8.314 joules per Kelvin, right? Because we're not worried about the moles right now, times the temperature, right? So that's 25 degrees Celsius. So that's 298 Kelvin times the natural log of 9.3 times 10 to the 9th in that case. And so delta G naught is equal to negative 8.314 times 298 times the natural log of 9.3 times 10 to the 9th. So that comes out to negative 56.9 kilojoules, right? Which, yeah, scaling up or whatever, right? So that's how you can get delta G in that case. Now for delta H, delta S, it's a little bit trickier, right? But we can then use the Van 't Hoff equation, right, to figure out what the delta H value is, because for that equation, what we have is natural log of K2 over K1 is equal to delta H over R times 1 over T1 minus 1 over T2, right? We know what the two K values are. We know what the two different temperatures are. We know what the R value is, so we can just simply evaluate all of those different parts in these cases. And so, if we start evaluating everything, right, and plugging stuff in, what we have is the natural log of K2, right, is I'm going to use the higher temperature, so that's going to be 3.3 times 10 to the 7th divided by K1, which is going to be 9.3 times 10 to the 9th, is equal to delta H over 8.314 joules per Kelvin times 1 over T1, which is 298 Kelvin, minus 1 over 398 Kelvin, right? That's going to be the T2 in that case. And so what we're getting is natural log of 3.3 times 10 to the 7th divided by 9.3 times 10 to the 9th. This expression comes out to 5.64 is equal to delta H over 8.314 JK times 1 over 298 minus 1 over 398. That's equal to 8.431 times 10 to the negative 4, right? So we move all of that stuff around, right? So we have negative 5.64 times 8.314 divided by 8.431 times 10 to the negative 4. So what we get is a value of negative 55.6 kilojoules, right? Which is basically what I have in the answer key there as well. All right, so now we have the delta H value, we have the delta G value. The last thing that we need is the delta S, right? And so we know, right, that delta G naught is equal to delta H naught minus T delta S naught. right? We know delta G, we know delta H, we know what T is. So we rearrange this equation, right? So what we get is delta S naught is equal to what is it? Delta G naught minus delta H naught divided by negative T in this case, right? So we get, what is it? Negative 56.9 kilojoules minus negative 55.6. I'm running out of space on that. Here, let me just go right here. Right? So then delta S naught is equal to negative 56.9 kilojoules minus negative 55.6 kilojoules divided by negative 298 Kelvin. So what we get is negative 56.9 minus negative 55.6 divided by negative 298 comes out to being 0.00436 kilojoules per Kelvin. And so if we put that into something that's more usable, right, like joules in this case, right, so all I have to do is just multiply that by 1,000. And so what I got is 4.36 joules per Kelvin, right? Which matches pretty closely with what I have right here, right? 4.049 joules per Kelvin, right? It's definitely, some kind of error somewhere in terms of just like sig figs and stuff like that. That's probably causing the slight difference. But yeah, right. So you get those right there, right? So you have the delta H value, right? So you calculate that using the Van 't Hoff equation, right? You get the delta G value by using delta G naught is equal to negative RT natural log of K, right? And then once you know those two, right, you can calculate what delta S is in that scenario. So now B, right, is the reaction endothermic or exothermic? Exothermic, right, because delta H is negative, so it's releasing heat. C, is this reaction spontaneous? Yes, right, because delta G is negative. If so, is it enthalpy driven or entropy driven, right? It's driven by both of them, right? So both the delta H is negative, so that's going to be, pushing the equilibrium to being negative. Delta S is positive, and so that means then that the negative T delta S term is always going to be negative as well, and so that's also then going to be contributing to the negative value. So this reaction right here is always going to proceed in a spontaneous fashion, right? They're always going to form those values as they go through. So that's A4. So I've got through everything that